So this is a short talk on the mathematics behind RSA if it essentially why it works, and also cases when it doesn't, like when there are bad implementations of it. So very brief overview of RSA. You probably already know this. Asymmetric cryptography, most obviously used in HTTPS. It's often used in conjunction with an ephemeral, sometimes elliptic curve Diffie-Hellman key exchange. In the SSL TLS handshake. This provides forward secrecy, which means that if the RSA private key is compromised at some point, the sessions from before shouldn't be compromised since they'd have used the ephemeral Diffie-Hellman key exchange. And RSA is therefore mostly used for just verifying the server certificate rather than key exchange. In fact, that's always the case with TLS 1.3. It provides more secure and faster TLS handshakes. To get actually onto the maths of it though, the first thing we're going to need to talk about is Euler's totient function. So the totient function is quite simple. It just finds the number of positive integers co-prime to another positive integer less than or equal to that integer. Very quick example, like 5 of 4 is equal to 2, because 1 and 3 are co-prime, but obviously 2 and 4 aren't. So in RSA, you only need to focus on the totient function for the product of two primes. So if you assume P and Q are prime, then phi of PQ is P minus 1 times Q minus 1. And the explanation of that is that if you expand that obviously gives PQ minus P minus Q plus 1, which implies there are P plus Q minus 1 integers that are not co-prime to PQ. And so this is true since if you divide PQ by P, the result is Q. So there are, which implies there are Q multiples of P that are less than or equal to PQ. And same if you divide by Q. So, so for instance, if you have phi of 15, I think that would be 8. Phi of 15 should be 8, and if and the numbers that aren't co-prime to that would be 3, 6, 9, and so on, and then 5, 10, 15. And in terms of multiples of 3, there will be 5 of them. In terms of multiples of 5, there will be 3 of them. The only repeated one is PQ itself, which in this case is 15. So that's where the subtraction of 1 comes from. So this is used in Euler's theorem, which is that a to the phi n is concurrent to 1 modulo n, where a is just co-prime to n. And the first part of this proof is to consider a reduced residue system modulo n, which is just a subset of the integers co-prime to n that contain phi elements, and none of the two elements are concurrent modulo n. In other words, they're totatives of n. So an example here is that the reduced residue system modulo 12 is 1, 5, 7, and 11. So first part of this kind of proof is that you'd want to show that A times R is concurrent to R modulo n, again, where A is co-prime to n. And so for instance, you can see that multiplying the system 1, 5, 7, 11 by 5 results in this, and this modulo 12 is 5, 1, 11, 7, which is just the exact same system, so they're congruent modulo 12 in this case. So the first part of the proof is to show that, first part of this proof is to show that AR contains integers that are co-prime to n, and that's quite easy to see because what you've got is two integers that are co-prime to n multiplied together. Of course, they're going to be co-prime to n. They don't share any, if neither of the products share any prime factors with n, then the overall product won't share any prime factors either. So continued with this, the next part of this proof is to show that there are no two factors, no two values in AR congruent modulo n. So to do this, we consider the contradiction where it's assumed that there are values in AR that are congruent modulo n. So in this case, A, B, and X are just co-prime to n, and you can consider A, B, and X as being values in R. The first line is just the assumption, basically, and the contradiction is in the last line, because x is co-prime to n and b minus a is not a multiple of n. So that's pretty much impossible. OK is obviously an integer. Doesn't have to be positive technically, but in this case it is. So now we've proven that A is congruent to R modulo n, since both systems contain finite elements that are co-prime to n, none of which are congruent modulo n. So that's that. And so we've proven this, and so then if we consider the product of all of the elements in R, which is just in the last line here, what we've shown is that that's congruent to the product of all of the elements in AR, and we can simply take the A out of there, so that's A to the phi n, and cancelling the product of all of the elements in R, we can simply get that A to the phi n is congruent to 1 modulo n, which is Euler's theorem, which is great. Except not exactly, just a quick proof that we can actually cancel the product. We can because the product is co-prime to n. So in this case, you can think of A as A to the power of phi n and x as the product. Since x is co-prime to n, so k must be a multiple of n, as seen in the second line. So kn over x is a multiple of n, because you can imagine cancelling the x and the k. So that means that A is congruent to 1 modulo n, or in other words, you can, the x cancels in the first line, and you get Euler's theorem. So the corollary of Euler's theorem that's actually used in RSA is this, which is that if you have x is congruent to y modulo phi n, then that implies that a to the power of x is congruent to a to the power of y modulo n. So this is because if x is congruent to y modulo phi n, you can rewrite that as x is equal to y plus k phi n for some integer k. And follow this, it's fairly basic modular arithmetic. And so that means from that you can calculate x to the e modulo n and retrieve x quite easily if you know e and phi n. You can do this by calculating the modular inverse of e modulo phi n, which you denote as d. And the modular inverse is basically just some integer d such that you multiply d and d, do that modulo phi n, and that's equal to 1. And you can see here that if you multiply, if you do y to the power of d, then you can, then that is congruent to x modulo n, and so that's how you retrieve x quite easily. A quick note that the modular inverse is only defined for values that are co-prime to the modulus, which is y needs to be co-prime to phi n. But it usually is. A is usually either, it's usually 65537. So it can be 3, but it usually isn't, I think. With a proper padding, it can be 3, but anyway, this is Fermat's factorization algorithm. I'm actually going to, I'm not sure how much time I have left, so I'm going to do a quick demonstration, hopefully, if this works. So you can see here we have the public key and an encrypted message. If I try and... So you can see the public key is just this in BM format, and then if I try to read the... yeah, obviously it's unreadable. So the first thing we're going to need to do to break this, basically what I'm going to do is try to factor the modulus. And from that you can retrieve the totient function, because you've got the primes that make up the modulus and so on. So this is a fairly basic script, just gets the modulus of the public key in hexadecimal format. It doesn't do much. Basically just uses the OpenSSL command and then does a bit of processing on the output in order to retrieve this. Not too incredible, but This is the Fermat's factorization algorithm implemented in Python. So if I were to enter the modulus here, factors it really quickly. I'm fairly sure that the primes actually used for this modulus, they are next to each other. I'm fairly sure the Fermat's factorization algorithm will only take one iteration if the primes are next to each other. But I'm not completely sure, so if you find a counterexample, please tell me. I'd be interested. You know, you've got the primes, you've pretty much broken it. Can't type for some reason. And we can just generate the keys using another Python script that I've written, if I can copy it correctly. And there we go. Okay, so now it should have written a new file called keyinfo in ASN1 format. It's not too interesting, I can't yet. It's got the public exponent, which was assumed to be 65537, the modulus, private exponent, P, Q, and some other stuff which isn't too relevant, but it basically means that it's basically because OpenSSL uses the Chinese remainder theorem in order to calculate something to the power of the private exponent. It's just slightly more efficient, really. So now we've got that. I'll actually put some commands here because I didn't want to memorize them. So we can do these copies correctly, as it didn't before. Convert it to DER format. Nothing too interesting. Then just convert it to PEM format. And you can see that there's a new file here called private key, which should be in PEM format. Good. And finally, you can decrypt the message. Really hope this works. And it worked. Good.